Welcome. Today we're going to present Raja, talk about how to use it and how it enables performance portability. We're going to interleave hands-on exercises with lecture materials, and our main goal for today is to hope that you learn enough to basically start using this in your own code if you want to learn more about how to use it. So during the tutorial, interrupt if you have questions. Just interrupt at any time, ask a question. We'll try to do the best to answer you. If it's more detailed, we may defer it to break time or later in the evening. We value your feedback. This tutorial is kind of a work in progress. We're continually updating it, expanding it, working in different materials. So if you have any comments, questions, suggestions, you'd like to see more of this, less of that, I was really interested in that, but I didn't really get it. Let us know, send us some feedback. We have a Google group linked into our GitHub project homepage. I'll put the URL up shortly. Or you can send us email at our project email list, raja-dev@llnl.gov. So anything concrete you have to say for feedback, we appreciate. So Raja is a library of C++ abstractions. They enable you to write single source loop kernels, and then you can run it on different platforms or with different programming model backends by recompiling your code. So for us, that's our definition of portability, to be able to write in your application code one set of source code and then rebuild it to run on different architectures. It does this by insulating your code from the details of programming model implementation aspects and hardware. And it supports a variety of parallel patterns, and the more detailed features that are more complex that we'll get to later in the afternoon enable different performance tuning options. So I'm sure people will start to wonder as we're doing this, as we get going through this, what's the difference between Raja and Cocos, right? We hear that a lot. They are similar in spirit. They're trying to address a similar problem. At the most basic feature level, I think they are largely very similar. We do some things in different ways. We have different API features. I think one of the more significant differences is how we provide different sorts of API tools for exposing, let's say, more fine-grained descriptions of CUDA thread and block layouts to application developers. This is something that our application teams wanted to be able to do for performance optimizations. And as we go through this, I'll try to point out some differences between how we differ from Cocos, but I won't really go into whether one way is better than the other. Oftentimes it depends on your application and your preference, and because Christian's sitting over there and I don't want to make him angry. So one difference between our projects is that Raja kind of grew up as a kind of a grassroots effort in the application environment in the weapons program at Lawrence Livermore. As we were preparing, our main focus over the last 4 or 5 years is getting those codes on our Sierra. We've come a long way since then, and our base of developers and contributors are people who actually work on those applications as well as people who are computer science researchers at the laboratory. And we try to focus on some specific design goals as we're building this up that emphasize usability and developer productivity. So we mentioned that we want to make applications be able to write single source kernels as much as possible. We want it to be easy to understand and use for all of the application developers that are writing code using Raja, because most of them are not CS experts or CUDA experts or how to tune performance on GPUs and that sort of stuff. Raja's not an all or nothing proposition. You can apply it incrementally in certain parts of your code. You can adopt it in different ways depending on what your needs are. And because we were integrating this into a large existing code base that has been under development for decades, and we need it to not be disrupted to meet programmatic deliverables, we don't want to force major disruption to this code base. So we promote kind of flexible implementations via clean encapsulation and allow applications to parameterize their applications with respect to how they will run by encapsulating types and specific objects and stuff in header files and then recompile the code by pulling in different parts of the header files. This will be a continuing theme throughout the talk. I will give kind of the different aspects of this stoplight chart, where we are in terms of development. The rows indicated by the column label, the column on the left, are the different feature sets that we think about Raja being part of, and that's kind of those sections we will use to break up this tutorial. And across the top are the programming model backends that we support. You'll notice the green columns for Sequential, OpenMP, and CUDA, because that's been our focus on getting on Sierra. Then there's a few bits and pieces that we've been working with to try to make workable. The column on the right, HIP, is a support layer for AMD GPUs. We've been working with AMD for about a year and a half developing that. We're evaluating a pull request right now, and that should be available in the next Raja release, probably the first week of September. Again, Raja is an open source project on GitHub. Later, depending on how you want to do the tutorial exercises, you'll have to go here to download the code, but it's pretty easy. Just go to github.com/LLNL. We're in the LLNL organization, and Raja is the project. And all of the materials that we have associated with our documentation, we have related projects, they're all linked off that main home page. A couple of items that you may be interested in is we have something we call a Raja Performance Suite, which is a fairly large collection of loop kernels where we have multiple implementations, both in raw forms for Sequential, OpenMP, CUDA. We have the AMD support in there, and then we have Raja variants. And we use these to assess compilers, how these variants compare in terms of performance, runtime. Vendors use these to shake out bugs in their compilers. This is used as a benchmark for DOE platform procurements. And we also have this Chai library, which is an array abstraction that automatically handles migration between into the execution memory space based on a Raja execution context. I'm not going to talk much about that today, but I'll point out why we did that later in the tutorial. So we'll eventually get to the exercises, but we prepared two options for you to be able to work. We have a Docker container that you can use on your laptops. We only have one for Macs. Unfortunately, we don't do Windows at this point because we really don't have any way to test it. We'll work on that in the future. We've also prepared build scripts and things to make it easy to build on Cooley and Theta at Argonne. You basically will just clone the repository. Make sure you give the -- recursive option to make sure you properly pull in the Git submodules that we have underlying Raja. You go into the top level Raja directory and then do a Git checkout of the @pesc 2019 branch that we prepared for this tutorial. And you'll have time, but please try to do this before we get to the exercises if you can. If you will use the Docker container, you'll need to be able to execute a Docker command on your laptop. So one common option that's fairly easy to use is the Docker desktop application. If you go to docs.docker.com/install, you can simply click. You might need to create an account and log in. I don't remember exactly how that works, probably not for the free version. You basically just download the DMG file and then pull it into your applications directory, and then you can execute this Docker command. And this will put you into a bash terminal inside the container where Raja is already compiled and installed. And from there, you can navigate around in the source code, edit files, rebuild it, and run it, and things like that. All right. We're going to go over a little bit of background material on various topics, kind of at a simple level, just to kind of ground people. You may have seen various pieces of this in Christian's presentation this morning, probably in Tim's presentation on OpenMP yesterday. But we're all here because we're interested in parallel computing, right? We all hope that our applications will run faster if we can execute many operations simultaneously, right? And parallel computing comes in multiple forms, right? There's instruction-level parallelism, where multiple machine instructions run concurrently. And this is generally the result of optimizing compilers, performing various optimizations and how they're supported by hardware. So the amount of parallelism that you have available basically depends on how many operations the compiler can determine that can be run simultaneously. There's also task or functional parallelism. I'm sure Tim talked a lot about this yesterday in the context of OpenMP. And you basically think about this as a directed acyclic graph where the nodes in the graph are your tasks, and you have lines between them with arrows indicating dependencies. So for example, here, in this simple cartoon, D, B, and C are tasks that can run independently, but none of them can start until A completes. And once A completes, they can all run. So you'd have three-way parallelism. So the amount of parallelism depends on how many tasks can run independently. And then there's data parallelism, and this is kind of the area where Raja focuses on, where you're applying the same operation to different subsets of data. So you have, think of this simple loop here. We're basically applying the same operation to each entry in different vectors for each loop iteration. And so the amount of parallelism is proportional to the size of the input data. And so when we think about running this in parallel, if we time its execution in serial where we run on one processor thread and it runs in T time units, we would hope that it would run in T over M time units if we ran it on M processes or threads, right, where M is less than or equal to N. But we'll talk about why that may or may not always be the case. So I think Christian probably went into this topic in more detail, but it's really important to remember that data dependencies can be a key inhibitor to parallelism. So you have to think about how you're accessing data and what the relationships are between the data that you're reading and writing as you're parallelizing your code. And one of the big problems that you have to think about and overcome is when you have data dependencies where multiple threads or tasks could be writing to the same memory location simultaneously. That's often referred to as a data race or a race condition. And that can cause an algorithm to produce non-deterministic results. You might get a different answer every time you run it. So for example, here's a loop where we're just summing up the entries of a vector. So what's the issue with this? Well, it's every loop iteration is writing to that sum scalar variable, right? So we're going to talk about this. Reduction is a important parallel concept. We're going to talk about that a little bit and how Raja reductions work a little bit later. Here's another sort of a loop. What's the issue with this one? Well, the way it's expressed, you're saying that the I minus first entry of X is computed before the ith entry of X. So this is referred to as a loop carried dependence. You have dependencies across multiple loop iterations. Oftentimes, in cases like this, you may have to think about rewriting your algorithm to enable it to run in parallel. Here's another example that's somewhat similar. It looks like we're computing a matrix transpose. We're exchanging the row and column index values of a matrix A. And the problem is that for the same column and row value, if we switch the order that we index them, they depend on each other. And finally, something like this. There's no real issue. All the loop iterations are independent, but you know, if you're not thinking about it, you might think there are. So this is a data parallel loop, and that the characteristic of a data parallel loop is that all loop iterations are independent. So I'm sure most of you have heard about Amdahl's law, and you know what it says, but just to emphasize the point, it gives us the maximum theoretical speedup we could expect to observe when we run a program in parallel. So it's given by this formula. S as a function of n is the maximum speedup of a fixed workload run with n processors, or n tasks. And then P is the proportion of sequential runtime, where we run it on one processor, of the parts of the program that can actually run in parallel, okay? And so we can expect this speed up to increase as we add more processors to a point. It's important to emphasize this says something about a fixed workload. As we add or more resources or take them away, we're still running the same amount of computation. And so you can't expect to continually gain additional speed up by adding an arbitrary number of resources. So for example, if only half of your application can be parallelized, P would be 0.5. Amdahl's law tells us that the most speed up you can hope to achieve would be 2x, right? You can make the parallel portions infinitely fast, potentially, but you're bound by the limitations that that serial section will always run sequentially, no matter how many resources you give to it. So basically what this boils down to, and it's important to think about if you're parallelizing an application, that really that proportion of the code that can be parallelized is the limiter for how much speed up you can hope to achieve. These are simple corollaries of Amdahl's law. So when we're parallelizing an application, how do we measure what we actually gain? Well, there's two useful definitions that are fairly simple to understand. One is called parallel speedup, and you can compute it by taking the ratio of sequential runtime for your program and then divide that by the time you observe when running n processes or threads, right? And then the efficiency is simply the ratio of the S sub n over n. And so when S sub n is equal to n, or equivalently E sub n is equal to 1, this is what we call ideal or perfect scaling. But in reality, we rarely see that, okay? And why is that? There's various overheads associated with parallel computing, and you probably, Tim probably talked about this yesterday when you say, launch a parallel region with OpenMP to run a for loop, for example, there's this fork and join operations, right? As the parallel region starts and then it ends. There can be significant overhead for that. Sometimes to the point where your code may run slower when you try to parallelize it than when you run it sequentially. There's also communication overhead. Most useful parallel algorithms, or many of them at least, have to exchange some data between the parallel processes or threads, and there's overhead associated with that. There's also load imbalance. For any parallel algorithm from start to finish, the runtime's always dominated by the process or thread that takes the longest. You may have other ones that don't take quite as long, but, and when they're done, they're just sitting there idling, not doing anything useful. And again, not all of your algorithms may be able to benefit from parallelism, so always keep Amdahl's law in mind. So here's something that you can think about, which is kind of interesting in your free time. So we mentioned that Amdahl's law tells us that theoretically it's never possible to see speed up greater than n for running on n processors, but in practice you can observe this. It's often referred to as superlinear speed up, and so there's a reference here in the slides that you can get on the ATPES website that explains some circumstances under why and when that can happen. It's also helpful to understand some basic architecture features, and so I'm just going to illustrate a few things with some simple cartoons as they relate to performance. So if you think about a modern multi-core CPU, you've got a collection of processor cores, and then you have this hierarchy of memory levels. Some of those levels are local to each core, like registers. You might have a couple of level of caches, and then some of the memory is shared across cores. You might have a shared cache, and then you have your local memory on the node, right? So data are moving up and down through this hierarchy as you're doing computation. They're moving closer to the core as they're being used, and then they move away as other data replace them, okay? So the thing to note, in general, memory capacity and access time decrease significantly as you move further away from the processor cores, and that's meant to be represented by the width of those blue bars, okay? So basically, to make things run fast, you want to keep data close to the processor as much as possible. Similarly, for GPU architectures, they have multiple, in the language of CUDA, streaming multiprocessors. AMD calls them compute units. They're really kind of the same thing. And they also have a memory hierarchy where within each SM you have let's say a level 1 cache, maybe a shared memory, or they're probably combined in the same memory space. And then you have caches that are shared by all the SMs, and then you have your main memory. And so you kind of have the same issues to think about when you're programming for a GPU versus a CPU. So in general, reducing memory motion, or at least controlling it and not doing excessive memory motion, is critical for good performance. And so you want to place data generally close together in memory when it's used together, okay? This is often referred to locality, and there's spatial and temporal aspects of that. And you want to consider data access patterns when designing algorithms, and I believe Christian went into some detail about that this morning. And he probably mentioned the fact that memory coalescing is very important for GPU performance. And that simply means multiple memory accesses are combined in single memory transactions. So with CUDA, for example, you want all 32 threads in a warp to read operands and write results in as few memory transactions as possible. And to do that, you want to avoid memory accesses that are non-sequential, namely where consecutive threads, GPU threads, are reading non-consecutive memory addresses, or you're doing sparse touching in memory, you're jumping around all over, or they're misaligned somehow with the hardware units that do the reads and writes. There's a couple of useful resources in the slides if you want to. The first one focuses mostly on CPU architecture, it's very useful, and the one on the bottom is also useful for GPUs. So a couple of other things before we dig into Raja. So like Cocos, Raja makes heavy use of C++ templates. Not that you have to be an expert in template metaprogramming, it helps, but at least to use it effectively, you have to understand how you use the templates in your code. Right, so here, this is the skeleton definition or a declaration of a for-all method that we're going to talk about in the next section for executing simple loops. It has 3 template parameters that are specified in that template parameter list. There's an execution policy, there's an index type or iteration space type, and then the loop body itself, okay? And so you specify those types when you write your code so that the compiler can generate the implementation of that function based on those parameters. And the way you would do that in something like Raja is you pass the execution policy as an explicit template parameter type, and then you pass, let's say, a range segment where you have a contiguous sequence of iteration indices 0 to n, and then the loop body, and then the compiler deduces the types of those 2 function arguments, whereas you specified the template parameter for the execution policy explicitly. And then we use lambdas to express the loop bodies, very similar to what Cocos does. And a lambda is simply a closure that stores a function and a data environment. And so a lambda expression has the form. I don't know to what level Christian went into this. I'll just keep this quick. There's basically a capture list in the square brackets. There's a parameter list in parentheses, and then the function body itself appears after that, surrounded by curly braces. So the capture list specifies how variables in the outer scope of the function call are pulled into the lambda data environment when it executes. There's 2 possibilities. You can, and very similar, in fact, behave similarly to how you express arguments to functions. You can either pass them by value or pass them by reference. Since by value is required for running kernels on a GPU, when using Raja reductions and some of other Raja features, we just recommend that you always use capture by value so that it's simpler and your code remains portable. And then the parameter list are arguments that are actually passed to the function body each time it's invoked. And so here, int I is simply the loop iteration index variable. And then another point to note is that when you use a lambda function in a CUDA kernel, regardless of whether you're programming straight CUDA or something like Cocos or something like Raja, you need this annotation, and it simply goes between the capture list and the parameter list. One last point is that by design, Raja does not provide a memory model, okay? That's one distinguishing characteristic between Raja and Cocos. Cocos provides a memory model to do specific things. So for Raja users, and this is something that we debated a long time with our users, and they decided that they wanted multiple options and different ways to do things of their own choosing, we decided not to force it, the issue on them, but to give them options if they wanted to use them. And so users of Raja in general have to handle their memory space allocations and data transfers explicitly. So in this simple, would be how you would execute a CUDA kernel where you're simply copying the vector B to the vector A. The question is, are you sure that A and B are accessible on the GPU? So you have some possibilities. If you're programmed in CUDA before, you know about CUDA malloc, CUDA memcopy, et cetera, the CUDA runtime library that provides those operations. You can also use unified memory, either software or hardware supported. You simply do the allocation using CUDA-malloc managed, and then it will page the data either to the host or to the device on demand as it's being consumed. And then we also have Chai, which can do this automatically without this other cruft in your code, and it works with AMD GPUs, and it works to enable different sorts of cache modes, let's say on KNL and things like that. So all of our tutorial exercises simply use, for the CUDA implementation, use unified memory, just for simplicity, so you don't have to worry about this particular issue. So we're gonna start simple by starting with simple Raja loop execution. So a typical for loop, if you think about it in C or C++, such as this, a DAXB operation, you're really expressing the loop iteration order, the data access, which entries in the array, because you're using the bare language. They're explicit in the source code, right? So if you wanted to change anything about the code, change the loop iteration order, or change the data ordering, you would have to change the source code. So Raja focuses on giving you ways to be able to do that without changing your application source code, but changing things you either pass to that source code as types for compilation or at runtime for iteration space issues, okay? So this is an example of how you might program that loop using Raja. So for all is that template method that I explained earlier, parameterized on a execution policy type. You provide an iteration space. In this case, it's a simple range from 0 to n-1. And then you pass the loop body as a C++ lambda expression. Typically, in our large applications where they have thousands or tens of thousands of kernels, they will develop a taxonomy of loop patterns in their code and define policies and iteration space objects in header files, and then propagate those throughout a large code base, right? So they're not thinking about writing this over and over and over for every loop, but just parameterize your code and then rebuild it in different ways. So those things might go in a header file. And the thing to note is that you have the same loop body. And that's one of the nice features of being able to use C++ lambda expressions. In most cases, not always, but in most cases, you can maintain the same loop body as how you originally wrote that C code, C-style code. And that's one of the things that was a big win in terms of the minds of our application users. So basic Raja loop execution has 4 core concepts, right? There's the execution template, in this case, the for all. There's the execution policy that you pass as a template parameter. There's the loop iteration space, object, and then the loop body, which are 2 arguments to this function, okay? So the method for all, that template method, will run the loop. The execution-based policy basically picks the programming model backend, Sequential, OpenMP, CUDA, et cetera, how it's going to run. The iteration space is something that you define at runtime. It could be a stride1 range, a list of indices, et cetera. In fact, if you follow some basic semantics of C++ iterable types, you can actually define arbitrary iteration spaces to pass into these things. And then the loop body is the C++ lambda expression. So one important thing to note, and this holds true for OpenMP or CUDA or many other parallel programming languages, you have to make sure that what you stick in the loop is appropriate for how you're parallelizing it, right? If you're running with CUDA or OpenMP threading, you have to make sure it's thread safe, or you don't have, data races and those sorts of things. So it's no different with Raja than it is for the other models. And so by changing that execution policy, you can choose how you run the loop and how the code gets compiled. These are defined at compile time, so recompiling the code, or changing this requires recompiling the code. And here are some examples of loop execution policy types. And they're pretty self-explanatory by their name. We'll talk more about these as we go through some of the examples. And so we provide a variety of execution policy types. Some of them are still in terms of optimization and how we're actually implementing things, or whether they're generally available. These are indicated with the double stars, our works in progress. One thing I want to point out that we have two sequential loop policies. One we call for sequential, which is seq exec, which basically forces strictly sequential execution. Most users put that in their code first to make sure everything's correct before they start parallelizing stuff. Then you can swap out that type with another one and see if you did it right. We have a loop policy, loop exec, which basically is the moral equivalent of how you would write a standard for loop and not put any like programming model pragmas or anything on it, and it basically would allow the compiler to decide which optimizations to apply to that loop, whereas sequential will force those optimizations not to be generated. And here's the stoplight, the row of the stoplight chart for. So basically we support all of this for everything, and soon HIP will be available. We mentioned reductions earlier. So here's an example of a vector dot product, C style, and we noted earlier that the issue with this is that every iteration is trying to write to that dot scalar variable. So if you wanted to parallelize this, what might it look like? So just as a simple illustration, suppose the loop length is 8. It's easier to draw pictures when you have small numbers. P equals 4 processors. You might think about implementing this as a tree-based algorithm where you can do at the first level 4 adds in parallel, where you're adding up the non-overlapping pairwise elements of the array, and then you follow that with 2 adds in parallel, and then finally 1 add. And if you notice, the height of that tree is basically the log base 2 of the length of your array. So 2 to the 3 is 8. So this is something you can think about. I'll put a reference up for this. There's something interesting called Brent's theorem that tells us how to bound execution time for algorithms like this. And in this case, it gives us a bound in terms of n and p with this formula of what we would expect the execution time to be. And here's a reference that you can look at. It describes the analysis of that result and how it's proved for this particular algorithm, if you're interested. So how does Raja support reductions? It's a little bit different. So Cocos has a distinct parallel reduce method. We currently don't. We're thinking about moving some things towards that direction where you actually pass in things as arguments. We're relying on the lambda capture. Most of our applications have preferred that to this point, but we realize that there are some potential limitations to that. So basically what happens here is the loop would now look the same as if you wrote it using, this is similar to the previous example where we write it replacing the for loop header with the for all stuff. But now instead of dot being a scalar double variable, it's this reduce sum object. So how does that work? Well, when you define it, you specify a reduction or a reduce policy, the type of the value that you're reducing, double for example, and then you give it an initial value for the reduction in the constructor, okay? And then when you're inside the kernel, updating that reduction value is basically what you expect. For sum, it's plus equal. For min, it's min. For max, it's max. And then after the kernel completes, there's a get method to get the value out, okay? So in our current, what we have now, you cannot access that reduce value and do something with it outside of the kernel. But we may change that in the future. We haven't really had a compelling reason to do it at this point. Another point, the reduce policy and the execution policy for the loop have to be compatible, okay? What do I mean by that? Because the implementations of how those reductions are performed and finalized in parallel depends on what programming model backend you're using. If you have an OpenMP loop execution policy, for example, you have to have an OpenMP reduction policy. If you have a CUDA execution policy, you have to have a CUDA reduce policy, okay? So we provide the full complement of these reduction policies for the different programming model backends that we support. And we support 5 different common reduction types. There's reduce sum, reduce min, reduce max. Those are all basically used the same. And then we provide a min-loc and a max-loc reduction. And what that basically gives you is the min or the max value plus an index, an iteration index where that min or max occurred. That's important for some implementations. And so we provide it. And the only difference in usage is that when you construct the object, you have to pass an initial value for that location index value. So another thing you can do is, because we're relying on capture by value for pulling the reduction objects into the loop body, you can put any number of reductions, right? Now, if you blow that out to try 50 reductions in a loop, there might be some performance implications. Yeah.
One question. Your in value, is that a neutral element, or can that be anything? So if I give the sum like 5 is my total sum, that will add it to that.
Yeah.
So it's not a neutral element.
No, you can do it. We have defaults. If you don't specify an argument, it will default to the neutral element for the type. But yes, you can start it anyway. So you can actually chain them together if you want running successive current. Yeah. So this is an example where we've defined all the different, an object for each of the different reduction types, and then we perform all of these reductions on a single array, sum, min, max. So you can do this kind of stuff if you want. So it's just an example of illustrate how that works, and what you would get is, so suppose A is an integer vector of length n, where n over 2 is even. That's just for making the example easy to describe. And we initialize that vector A as 1, minus 1, 1, minus 1, all the way across. It would end with minus 1, because n over 2 is even. And then we replace the center, or middle value at n over 2 with 10, and the values on either side with minus 10. So it's pretty easy to compute what all of these reduced values would be, but I just want to make a point on one of these is, so the sum would be minus 9. It's easy to check. Min and max are obviously minus 10 and 10 respectively. Max loc is obviously n over 2 because there's only one max value. But min loc could be, that index value could be either n over 2 minus 1 or n over 2 plus 1, depending on how the reduction completes in parallel. So it's important to note that the results you will get out of any reduction in parallel, even OpenMP or whatever, you may not get the exact same answer all the time. So you have to be able to make your code robust enough to deal with that. And so here's the stoplight chart of our reductions, okay? The OpenMP target reductions are usable. There's just, we're working through some performance issues at this point. So now we're going to do a couple of hands-on exercises. So going back to here, depending on how you want to use the code, I don't know if people have started doing this already, maybe try to get set up depending on what choice you want to have. Do most people have Mac laptops, or do we have Windows laptops in here? Windows? So yeah, so your option is only the, right. So, okay, so when you're using the Argonne machines, we have some build scripts, okay, in the Raja scripts ALCF builds directory. Each script has some instructions in it to basically get on a compute node for that architecture. And then once you do that, you execute those, it's usually like 1 or 2 commands. And then go back to the top level Raja directory and just enter the name of the script for the machine you want to run, and it should just build. So you probably didn't do all these steps, right? Yeah, so you have to run the scripts from the top level Raja directory. Yeah, so there, if you look in the script, there's a couple of comments that basically say how you get on a compute node. And then after you run the script, you cd into the build directory that it creates that's named for the machine and compiler combination, and then type make -j, and it should just build. And then you can type make test to check and see if everything worked right. So basically, regardless of whether you're using the Docker container or you're running on one of the Argonne machines, the exercises basically involve, I'll describe what the exercise is. You go into the exercises directory. I'll say what file specifically there is. You would edit that. The tasks are going to be basically adding Raja code. You go into the build directory that was made when either in the container or when you ran the script, the build script. recompile the code by typing make, run the executable, which is in the bin directory in there. Each one is labeled for the execute. So if you're doing exercise 1, if you type ex1, tab completion, you will see what the executable name is. And then when you run it, it will tell you whether it'll give you pass fail for the different pieces, right? You can do this repeatedly. You can work each piece or try to do them all. There's also functions in the script where you can print out results. You can see what you're doing. And then all the spots in the files where you have stuff to do, they're indicated by these comments that have to do and exercise all caps in them, so they should be easy to find. So the first exercise is in the file Raja exercises, tutorial half day, exercise 1, vector addition, okay? In that file, you will see C-style, sequential, and OpenMP implementations of that simple algorithm, okay? The task of the exercise is to implement sequential and OpenMP variants of this using Raja for all and the right execution policy. If you look in that file, we've already done the sequential one, so this is largely a cut and paste exercise where you would take that code, cut it, put it down into the OpenMP section, which is guarded by OpenMP guards. In case you don't have OpenMP enabled, the code would still compile, and then pick the OMP parallel for exec policy. And then if you have access to CUDA, you're running on Cooley with the NVCC compiler, you can do the CUDA one. And if you want details, if you go to the Raja GitHub page, go to the user documentation, there's a pull-down menu on the left. If you go to the feature section and policies, you will see a table describing all the execution policies that you could use. So you could try different things out. So basically, as I mentioned earlier, each one of these exercise files for you to fill in is also accompanied by another file in that directory that has _solution in it with all the code sections filled in, so you could compare those files and see what you're supposed to do, okay? So in this case, there would be a file called exercise1 vector addition _solution. So basically what you should be putting in your code is something like this, where you're just plopping in the appropriate execution policy. All right, so I'm just going to keep moving on. We can talk more about this at the break. But again, there's a file with all the solution in there that you can just, that's what you're basically supposed to do. So the second example is basically doing the same thing, but using a Raja reduction to compute pi, approximate pi, using this integral identity. You'll see, so you're doing a Riemann sum, you're summing up using you will see C-style and OpenMP loops. You basically use the same loop bodies, but you make a Raja for all loop, and you make the reduction type above that to accumulate pi, or approximate pi. Since we're running a little low, I would suggest that here's basically what you've done. So this is in the C version, okay? You do the reduce sum like we did before, and this will give you, and then you pull, I didn't put the code in here to pull the value up, but that's good. So you can also look in this file, which has all the answers to the exercises if you want, okay? Are some people making progress? Don't worry if you're not, if it's not all working. We'll help later. We're not expected to get through all this. All right, Christian got 100. All right, so I'm going to start going on to the next topic. You can keep working on things as you want. So we're talking about iteration spaces, segments, and index sets that we mentioned earlier. So a Raja segment, we've seen this range segment a couple of times in examples, and it basically, so you think of a segment as a collection of loop indices that you want to run as a unit, right? So there's contiguous range segments, we have strided range segments, we support lists of indices, which are effectively indirection sorts of things. And then we also have index sets, which are containers of an arbitrary number of arbitrary segment types. And then you can execute this kind of a pattern with one call to, let's say, a for all method, okay? You might be wondering why we do this. I'll get to that in a minute. It's very important for certain types of applications. So we've seen the range segment thing. When we use this and pass it in as an argument to one of these things, you could do something like this and just put a print statement in here to see what the iteration indices are, print out I, and you would see it would go from 0 up to n minus 1, right? Stride segment is basically the same, where the third argument is now a stride. So this would run the loop indices 0, 2, 4, 6, etc. You can also do things with negative strides and negative indices. So for example, starting at n minus 1 down to minus 1, right? The right side is always it's a half open interval. Stride of minus 1, it would run a loop in reverse, okay? N minus 1, n minus 2, et cetera, down to 0. So one thing to note is that this range segment, range stride segment are actually type aliases. We have underlying implementation is a typed range segment or typed range segment. The specializations are used as a convenience where we pass in the parameter Raja index type, which is something we use internally, or we define as a useful parameterization for convenience. It's basically an alias to std pointer diff underscore t, which iterators in C++ often use to compute differences when they're updating. It's appropriate for most compiler optimizations. You typically want to stay away from unsigned integer types when you're writing for loops and stuff, because for some reason some compilers don't like that. They'll produce code, they just won't optimize it as well. So a list segment that we mentioned, you can have any set of indices. So the way you would do that is you would create a type list, or define a type list segment type. I'm just you don't have to use these using directives all over. I'm just doing that to get people thinking about when you're putting this stuff in a code, it's very helpful to parameterize your code like that, put these definitions in a header file, and then you can propagate changes throughout your code, right? So if you define an array of, say, 5 indices, 10, 11, 14, 20, 22, you construct a list segment object by passing that array and the number of entries into the constructor, okay? And then you can pass that in just like a range or a range segment, stride segment, into the execution template, and it'll run those indices. One thing to note is if you've ever done code with indirection arrays, you would typically see, let's say, some other array and sub I inside of here. The Raja internals, when we do these list segments, take care of that, so you don't have to have that in your inner loop body, and that enables us to be able to have the same loop body work for different types of segments, okay? And an index set may contain multiple segment types, as I mentioned. So here's an example where we create a range, 0 to 7, a list, same as we did on the previous slide, and another range going from 24 to 27. We create a typed index set where it's a variadic template, meaning it can take any number of template parameters. You have to specify the segment types when you declare that object, so it's known at compile time. Here we say it will hold potentially, it doesn't have to hold one, but it potentially can hold a range segment type and a list segment type. And then you use kind of pushback semantics to stick those things onto the index set, and what you get out of it is a single iteration space partitioned into 3 segments, like that down there, right? And again, the segment types must be given at compile time. The only difference between using these and just single segments is that the execution policy is a 2-level policy, right? So one characterizes how you iterate over the segments, right? You have to, hit each segment, and then one is how each segment executes. And so these outer segments we distinguish by an underscore segit name, okay? So why do we do this? Well, multi-physics code, especially multi-material codes, which are very important to our program, use indirection arrays a lot. They have unstructured meshes. They've got different material regions at different zones on a mesh. When you start adding all these indirection arrays, you impede a lot of optimization in your code. You have more instructions, all these integer operations. You're pushing more data through memory. But oftentimes, it looks like you have this large indirection array. There might be huge stride 1 ranges embedded within it. And so what we can do with this is we can encapsulate that index space as an index set of different types, and the compiler can generate optimized code for those stride 1 ranges, potentially vectorizing it, and do whatever it needs to for the other one. So basically, you get some performance benefits to this, okay? And again, supported for everything, and soon, yep. So as an example of how this can be beneficial, consider a mesh like this. This is a kind of a common operation you see in kind of staggered mesh hydrodynamics codes. At each vertex on the mesh, you want to compute the average area of the 4 surrounding elements, okay? There's a notion of a vertex area, okay? Those 4 green elements surrounding the black circle. So and the way most of these algorithms are always written is because you're doing stuff inside the zones, but while you're doing this or inside the elements, is you iterate over the elements and you shove out 1/4 of its area to each of its surrounding vertices, okay? But the problem with that is, and it could be written something like this, right? I iterate over all of my elements. I have this array that enumerates the vertices around each element. That's what this thing is. It's just 4 successive elements. This is where the indirection might occur, enumerating the vertices around there. And I add 1/4 of the area of the element to each. But this won't work in parallel because there's a data race at each vertex, right? 2 neighboring elements share vertices, could be writing to it, right? So one thing you can do, and some of our applications actually do this, is you can break this apart into multiple segments, right? Where represented 1 for each color or number. And if you notice that everything within each color or number that have the same number don't have any shared vertices, okay? So you can parallelize over all the blue ones, all of the orange ones, all the red ones, all the purple ones, okay? And the results will be reproducible because each of those is then data parallel. All the loop iterations are independent. So the third exercise, in the interest of time, I'm just going to go through it, and you can look at it later, you basically have C-style sequential versions and OpenMP versions where we do that sort of a thing. We partition the elements up into 4 sets of array indices, and then we run the loop 4 times, okay? So using an index set, what you would do is you would, we've got a segment type is defined in the code to be a list segment. But basically, and we've got these 4 arrays that we use in the C code to enumerate. So these are enumerated for the 4 vertices of each one. We create an index set with 4 segments, and then we run this. And note that this code looks exactly like the sequential kind. The only thing is the indirection is not as complicated, and this can run in parallel. You could even launch this as 4 different CUDA kernels, for example, okay? And you can see exactly the full implementation in that file. Oops, wrong direction. So now we're going to move on to another topic, atomic operations. We can talk over that other exercise later if people want to, but it should be fairly straightforward. You can actually literally compare the sequential or OpenMP C-style implementations with the Raja version and see what's going on. So Raja provides atomic operations that are portable. And atomics are basically, they perform updates at specific memory addresses, either write or read, modify, write, in such a way that only one thread or process at a time can do the update, okay? So let's say you have a pointer to some values, X and Y, a pointer to each, an array basically, and you want to atomically update in a loop, adding 1 to X sub I and atomically adding 1 to y sub I, depending on what you're doing. You could simply do it this way. And you're assured that this will always work in the sense that you will have no data races. Your results may be different depending on who gets there first. There's still that issue, but you won't have, say, one thread reading a value, another one writing to it, and then that first one writing back to it where that other read isn't seen, okay? So remember, in that second exercise that we talked through, or that you were working on, you approximated pi as this Riemann sum using this formula, and we used a reduction. You could also use an atomic operation to accumulate the sum for pi, and that would prevent multiple threads from attempting to write to the same memory address. And so how does that look? Basically, it looks the same as you had before. You don't define the reduced sum object. You basically, inside the loop, where you're adding the subinterval height times width of the subinterval to pi for that integral atomically into the sum pi, okay? And this has to be an address, right? It can't just be a scalar value. The code won't compile. It has to be an address. So you could do that same problem using atomics, okay? We also have an atomic policy for built-ins, which means they will insert compiler built-in atomics for whatever compiler you're using. We also have an auto-atomic policy, which basically picks the right thing for you depending on what your execution policy is. So for example, if you're running with OpenMP, it would insert an OpenMP atomic operation. If you're running an CUDA kernel, it would insert a CUDA atomic operation. And then, I don't know, did you talk about the array ref or atomic ref thing at all in yours?
No, I didn't.
Okay, so anyway, in C++20, there's going to be an atomic ref implementation, basically to support atomics on arbitrary memory allocation or locations. And we basically prototyped something that modeled after that interface. And so what you can do here is you can say, okay, I have a scalar double value 2. I wrap this up, the address of that, it holds that address in an atomic ref object called sum, and then I can do things like postfix, increment, prefix, increment, plus equal sorts of things, and it will work in a CUDA region, for example, because we're using the autoatomic, work in an OpenMP region, et cetera. So the result of that would be 2 plus 1 plus 1 plus 1, or 5, okay? That's just, this will be supported in C++20, and we just provided something that's similar to it, so people could swap out the name with the stood atomic ref when it becomes available. Yeah.
Your policy larger automatic that hasn't anything to do with the actual atomic semantics, right? It's not the acquire release that collects the sequentially consistent, right?
Yeah, no, it's basically what atomic operation is going to imply internally. Like, is it going to be an OpenMP atomic or a CUDA atomic or whatever?
Right, so it's not the same as in C++, the character addition was there.
Yeah, exactly. Yeah. And so we provide a variety of atomics, pretty much everything you would find useful. We have arithmetic, add, subtraction, as we saw, min, max, varieties of increment and decrement, bitwise, logical, replace, exchange, compare, and swap in this stood atomic style, or atomic ref style interface. And so these work with everything except our SIMD policies at this point. We haven't really encountered a need for that. We're not sure exactly how we would do that. But if we want to try the exercise 4, the idea here, this is pretty simple. Basically, you have an integer array of length n. Each of the values is from the set 0 to m minus 1, where m is less than n. And you want to build an array of length m where each entry is the number of occurrences of the value I in the array, okay? So that's in the tutorial exercise 4. There's C-style and OpenMP atomics of this histogram calculation, and the idea is to basically do a Raja for all with OpenMP or Sequential and then pull in the right atomic operation. okay? And if that policy page includes the execution and atomic policies and stuff, just kind of scroll up and down the page to find what you're looking for. But it should look something like this, okay? So you can actually take the C-style code and use bits and pieces from that and cut it and paste it into, you know, what you were doing before. The only difference here is we've replaced the C-style loop header with the Raja for all call, and then whatever atomic was used in the C-style code. Of course, sequential, there is no real atomic for that, but there's one for OpenMP, and then this would just be basically a call to the atomic policy. So at the end of the day, you have this array with a bunch of values in it, and you've computed this histogram which says how many occurrences of each of those values you have. So if anybody wants to work through that, I'll give you a few minutes to do that. Okay, so as to finish up a section before the break, which starts in about 10 minutes, I'm going to go into the next section, which is about scan operations. So Raja provides portable scan operations, and scans are a very important building block for parallel algorithms. They're basically a key primitive to convert things that look like they're inherently sequential into a parallel implementation. They have a variety of applications that I've listed here. There's a useful kind of seminal reference on how to use them and what they can be used for in this link here on the slides. I encourage you to look at. Very interesting paper. And so prefix sum, you may have heard of, is kind of the most common scan. And the way that works is you have an input array of values, here an integer array, and then you put into an output array a sequence of partial sums where the first entry is the first element, the next entry is the sum of the first two, next entry is the sum of the first three, et cetera, okay? So that's given by this inclusive scan here, where you basically, there's a policy. These execution policies are exactly the same thing that you would use in a for all, right? So you could run this CUDA, OpenMP, or et cetera. You pass the address of the input array, and then basically, plus the n, so you in plus the n. It's kind of like when you do C++ programming, you go end, or something not equal to end. It's like 1 past the end. And then you pass the starting address of the output array. Okay, so you have to make sure that these arrays are allocated to the appropriate sizes. But if you have a sequence of numbers, let's say n is 10, of in like this, the inclusive scan, basically, here's the first entry. We add the first two, we get 7. We add the first three, 7 plus 2 is 9. 9 plus 9 is 18, et cetera. That's a parallel prefix sum scan, okay? Then there's also an exclusive scan, and the only difference is it looks the same as the inclusive scan, except it shifts everything one slot to the right in the output array and sticks the identity of the operator. Here we're doing plus, so 0 is the identity of the plus operator in the first slot, okay? We also support in-place scans, where you basically do everything in place in the input array, okay? And it looks the same. You get the same result, inclusive and exclusive scans, but you put the underscore in place. You basically pass the input array, and it puts the result back in there. You don't need an output array, okay? And we also provide different operators you can use. So if you don't provide any operator, you get by default plus, so you get a prefix sum. But you could also do a minimum operator. So that's the same array we started with. If we do an exclusive scan with that min operator, we get the inclusive scan shifted to the right. So the min of whatever in 8 is 8. Min of 8 and minus 1 is minus 1. And then we keep going until we get some minus 3s because we hit this minimum. And then this value, what is the first value? It's basically, because it's an exclusive scan, that's the identity of some operation. Well, the identity, in some sense, of the min of an integer is basically the largest integer, because you're always going to take the minimum of that with any integer, and you're always going to get that any integer. So it's kind of the identity operator, okay? Does that make sense? All right, so we support scans for everything except SIMD and OpenMP Target. In fact, OpenMP Target is just starting to support scans in the OpenMP standard with the OpenMP 5 standard, although it's a little grungy in my opinion, but we'll see where it goes from there. So before we break, I just want to talk through a kind of an cute little usage of this scan operation to kind of make it concrete. So this is called the line of sight problem. We're going to be at the break right when I get through the description, and then Arturo is going to take over after that and talk about some other stuff. So this is an exercise you can also work if you want. So basically, you're given a terrain map, right? Imagine we have a terrain map on the floor here, so it's two-dimensional. And we pick a point X, an array, okay? And then look at what the terrain looks like along that ray, okay? And so the problem is, given this observation point and the point on the surface, and a set of points along that ray, which are the points that I can actually see from X, okay? So if the terrain goes up and down, you're not going to be able to see everything. So for example, here I can see the blue point above Y1, but I can't see the red point above Y2 because this hill's in the way, okay? So the problem is to figure out, given a discrete set of points, which ones can I see? So the definition of when a point is visible is basically a point along the terrain is visible if and only if no other point along that ray between the point you're looking for and your observation point has a greater vertical angle, right? So going back to the blue and the red point, I could see the blue point, but I couldn't see the red point. And why is that? Because the blue point has a larger vertical angle than the red point, so there's a point between Y2 and X, namely at Y1. In fact, there's a whole bunch of points that have a larger vertical angle than this angle, the red angle. So I can't see them. I can't see this guy, but I can see that guy. So how would you, this is actually described in that Blelak paper that I mentioned. So basically the way to think about solving this algorithmically is we define a scalar variable to be the altitude at the point X, and then we define a vector, let's call it alt for altitude, at each point Y, right, along some ray, think in terms of each of these boxes, is the altitude of that point. So we have this altitude vector where we've basically discretized the terrain into a bunch of piecewise constant segments, okay? And then we have a vector of distances between X and each of those points along the plane of the ground. And then we compute the angle at each one of those points or in each one of those intervals. And that's simply the arctangent of the difference in altitude at the point yi on the surface at a point xi minus the altitude at the point x divided by the distance, okay? So you can do this in parallel with just a regular parallel for loop, okay? And then to figure out which points you can see, you actually do a scan operation on this angle vector using a max operator, okay? Right, so you will have a bunch of max values where at any point it's the maximum angle at that point. And then you can use that to compare to the original angle vector. And so if the original angle vector at index I is greater than or equal to that max angle vector, then you can see that point Y. Otherwise you can't see it, okay? So you can actually do this by, this is the exercise 5, which shows you how to use scans. So you're basically what I'm saying is you take the angle vector, you create an exclusive scan or an inclusive scan on that using the maximum operator, and then you plug this into this algorithm and you're saying, okay, if the angle at that point to the point on the surface, observation point, compared to the max angle, it's greater than, I can see it, otherwise I can't, okay? So that's kind of the exercise 5 to make the scan operation sort of a little bit more concrete and how you might use it.
So I'm going to start transitioning over to talk about multi-dimensional arrays, more complex loop patterns, and start talking about some of the more advanced features that Raja has to offer. So I'm going to start off by talking about this example. This is a matrix multiplication example. So matrices and tensors, right? These are examples of multi-dimensional arrays. These objects are all over the place in scientific computing. You see them in linear algebra, machine learning. And these guys are most naturally thought of as multi-dimensional arrays, but in practice, they typically get allocated as one-dimensional arrays. The consequence of this is that there has to be an index calculation to transition from multi-dimensional indices to one-dimensional index, right? And if you guys want to stop me at any time, if you guys want to chat, feel free to do so. So we find that a little bit cumbersome. So in order to alleviate that computation, what Raja has to offer are views and layouts, right? And the idea behind these views and layouts is to simplify multi-dimensional indexing patterns, right? So the way these work is you allocate your array, right? With a view, you template based on your data type, and you also template on a layout. So for now, we can just think of the layout as a type that holds the dimensionality of our array. And then the constructor simply takes the pointer and the extent of the dimensions of our array, right? So in this case, we have a two-dimensional array with extents n by n. So by encapsulating our pointer into this object, this leads to data indexing that is much more intuitive, it's more natural, and less error-prone, right? So semantically, it's easier to read. So the views and layouts support any number of dimensions. You can consider taking an n-dimensional tensor, or n plus 1, and you can pop one of these into a Raja view, and they would work as you would expect them to, right? So you have your view, you template on the data type, your layout holds the dimensionality, in this case n plus 1, right? And in your constructor, you simply pass in the pointer and the extents of each dimension. So in the bottom two, I have examples of using the view to iterate over different indices. So by default, the outermost index is going to have stride 1 data axis, and then as you move from right to left, you increase in axis stride, right? So in the bottom, J, the stride for that is n times basically the strides to anything on the right. But of course, we believe in flexibility, so if we don't like that index permutation, we can create our own permutation. So Raja provides methods to make layouts for other indexing patterns, right? And you can do this using the make permuted layout method. So to change the permutation, you simply have to provide what the extent is of each dimension, and then in a separate array, indicate which indices should range from the slowest to the fastest. So using this construct, we can create a 3D layout with indices permuted. So index 0 then has extent 5 with stride 1. Index 2 has extent 11 with stride 5. Index 1 has extent 7 with stride 55. So as before, we can simply take our permuted layout and pass it into a Raja view, and then this changes the way we're indexing into our data, right? This is more customizable, and this is equivalent to indexing as we have there in the in the vector. Another feature that we have is we can add offsets to our layouts. So for example, if I want to allocate an array of size 11, but I don't want my indexing to start at 0, right? Suppose I want to start my indexing at -5 and end at 5. I can use the make offset layout method to generate an offset that I can then pass into a view and do exactly that, right? So you make your offset layout, you pass it into the view, and then when you're actually indexing into your view, you can start at -5 and end at 5, right? So these offset layouts are very useful for index-based subset operations, such as halo regions. So if anyone ever does any type of finite difference calculations and you have to do any type of parallel computing, you usually have to add a halo region. So there's a couple important notes about Raja layout types. So all layout objects have a permutation, right? There actually is no Raja permuted layout type. For example, any layout, if we don't specify the layout, you'll end up with the default layout, but, I'm sorry?
No permutation.
Oh, there's no permutation, that's right. But we can custom out the permutation using the make permuted layout method. All right, so the other variant of layout we have is the offset layout type. So this is a special type because it has to hold out the layout. It holds the permutation, and it also holds offset information. And here's a couple of examples of the offset layout. Right, you can just use it to make to add offsets, or you can make a permuted offset layout. Yes.
If you always can create this permutation, which seems like a runtime information, does that mean that none of your layouts have compile times right on any of the dimensions?
You can add actually a compile. You can add that.
There's an optimization for that.
Okay.
Right. I don't think we show an example here, but that's definitely an option. Yeah, and that would be a performance improvement.
We had that question in the C++ standard layouts.
Yeah, so we give that as you can do that.
Okay. All right, cool. So I would like to keep things interactive, so pop quiz, everyone. So offset layout quiz. Okay, so if I define an offset layout, this is two-dimensional, right? What index space does this layout represent? So it's a two-dimensional index space, right? You're going to range from -1 to 2 by -5 to 5. Second question. So which index has stride 1, right? So if I take this layout and pass it into a view, which of my indices will have stride 1? Right, so we didn't specify a permutation, so by default, the rightmost will have the stride 1. Okay, so what is the stride of index 0? So the stride of index 0 is 11, right? And this is because index 1 has the extent of 11. Okay, so let's try a permuted offset layout. So if I construct a permuted offset layout in this fashion, what index space does this layout represent? So we haven't changed anything from before, so it's the same as the previous example. It's a two-dimensional index space. It ranges from -1 to 2, and it's by -5 to 5. So which index has stride 1, right? So we added a permutation. So now index 0 has a stride 1, right, due to the permutation that we added. What is the stride of index 1? So now index 1 has a stride of 4, and this is because index 0 has the extent of 4, right, -1 to 2. So under the hood, what's actually going on here is that these layout methods are actually doing the conversion between multi-dimensional indices and linear indices. So you can actually just take the layout, right, create an object. In this case, we've created a 3D layout with extents 5, 7, and 11. And we can use it to convert from multi-dimensional indices to one-dimensional indices, right? So if we were to plug in these values into the layout, to the parentheses operator, the value of lin would then be 188, right? And this is just a simple calculation. And we can go backwards too. We can go from the linear index to the three-dimensional index. And we can do this using the two indices method. So we simply plug in 191 into the 3 values, and then out we get that ijk is 2, 3, and 4, right? And you can do the calculation to get 191 back. Yes?
Is that just after whatever number? Oh, no.
Yeah, you know what has the stride one, right? So you know what has the stride property. Yes, that's time. It's based on the strides.
Sorry.
Is there overhead to that version?
I don't know.
That overhead is about 100 index operations. Also simple integer operations because you do diffs at once. But you do
Actually, there's ways you can actually optimize that by writing those with interesting formulas. Formulas for old recessive mod. We actually dug out some old numerical analysis papers that had some cool algorithms. And they actually make a difference in performance. There was a question here.
Yes.
Well, you get, you put in things in 10,000.
Oh, but it's outside the bounds of the array.
I actually don't know. But we have laptops. But maybe we can try it sometime, right? Yeah. Yeah, we'll try it. I'll get back to you. You had another question here?
Just want to make sure sort of permutation, that the sort of index that go from left to right, and then, is that right?
So
you do permutation, you list the numbers, 0 reference to the leftmost.
So whatever is rightmost is going to have the shortest stride.
Right. But then when you do the permutation, when you say 0, 1, 2, that's 0 reference to the leftmost.
Yes, that's right.
So is there a reason to, personally find this sort of a flip a little bit up?
Well, it's kind of the default C style.
Okay.
If you just define the multi-dimensional array as C, this is
Okay.
Fortran ZIs.
Yeah, that's right. Yeah, okay.
But with the permuted layouts, you can just flip them around or do whatever it is you need to. That's right. So Raja supports using layouts essentially across the board. And although we haven't integrated the HIP backend yet, I would expect that it would just work. So how about we try it out? So exercise 6, 5-point stencil, right? So in this exercise, consider a simple 5-point stencil computation on a 2-dimensional Cartesian mesh, right? So essentially your stencil's across. Suppose the matrix A has an entry for each element on the mesh interior, and matrix B has an entry each element on the mesh interior plus a halo layer. So it's 1 element wider around the interior. So what we want to do is we want to write a stencil computation as a nested loop and use Raja views to write the loop body naturally in this manner. So it looks like semantically, it looks more mathy, if you will. So we're going to take some time digging into exercise 6. It's under the exercises folder. There's 2 parts. The first part, part A, assumes that the column J loop indexing is stride 1. Part B is going to assume that the row I loop indexing is stride 1. So the exercise here is to implement and run sequential variants of part A and part B using Raja views. Right, you've seen this before. The goal of the exercise is for you to learn the mechanics of creating and using Raja layouts and views. And as before, you can check your answers. There'll be you can print them out. So your actual loop body should look like this in the bottom. Okay, so let's take like maybe 10 minutes to do that. And me and Rich will walk around. If you guys want to flag us down, feel free to do so. So if you worked out exercise 6, or your solution, at least for part B, should look something like this. If you didn't get it, don't worry about it. The solution is there. You can feel free to talk to me or Rich at any time after the session. But just to move on now, we're going to be looking into more complex loops and advanced Raja features. So I'm going to start off talking about nested loops and what Raja can do for nested loops. So starting off with an example again, let's look at matrix-matrix multiplication, right? This is an example of a numerical routine that requires nested loops, right? You know, we all know matrix-matrix multiplication. You loop over the rows, the columns, you do a dot product, and you write out to your output array. So if we want to create a Raja variant of this, from what we've covered so far, what we could do is nest Raja for all statements, right? We can take our top two loops, convert them into Raja for all methods, and because I'm not a fan of index calculations, we replace the index calculations with Raja views here. But as it turns out, this actually doesn't work too well. The reasons for this is that each loop level is treated as an independent entity, right? So if I want to parallelize both the row and the column, it's pretty hard to do that with that framework. We can choose to parallelize the outer row loop using OpenMP or CUDA. But then the problem is that each thread executes the code in the inside sequentially. If we choose to parallelize the inner loop, then that introduces a lot of unwanted synchronization, right? So if I want to parallelize it using CUDA, then I'm launching a kernel at every iteration. So if we want to also do things like loop interchange and other transformations, then that requires changing the source code of the kernel, and that totally breaks the Raja encapsulation model, right? So for these reasons, we don't recommend using Raja for all for nested loops. What we recommend instead is using the Raja kernel API. So I'm going to break this down in the next series of slides, but I want to point out that rather than using the for all method, we're now using this Raja kernel method. And you can note that the lambda expression for the inner loop body is the same as before. So there are 4 key components to the Raja kernel interface. And this is designed to be analogous to the Raja for all method, right? So first, there's the execution template. There's the Raja kernel portion of the code I showed in the previous slide. There's the kernel execution policies, right? And we had that under kernel pol. We have kernel iteration spaces, right? So we have multiple loops, so we have to provide an iteration space for each of those loop levels. And then we also have the kernel body. In this case, we have 1 lambda, but Raja kernel actually has the capability to take in multiple lambdas, and this is something we're going to visit throughout the talk. So in this example, we illustrate that each loop level has an iteration space and loop variable, right? So we have to provide, because we have 2 loop levels, we have to provide iteration spaces for each of them. In this case, the column range and the row range, and we have an accompanying loop variable, right? So the column and the row, right? So it's important that the order and types of tuple items and lambda arguments match. So the way you can tell which for statement corresponds to each loop level is simply by looking at the integer template parameter. Right, so the integer template parameter in each for statement indicates the iteration space, the tuple item it applies to. Right, so in this case, 0 corresponds to the column for loop, and then 1 corresponds to the row for loop. So if we want to do some sort of loop transformation, in this case, reorder the loops, all we have to do is change the execution policy. We don't actually have to touch the algorithm code. So in the top example, we have a policy that's going to take our row loop and treat it as the outer loop, and then the column loop is going to be the inner loop. If we swap the statements, then the outer loop is going to be the column loop, and then the inner loop is going to be the row loop. Right, so this is very similar to having CSAL implementation and going in and manually reordering the loops.
Question.
Yes.
Does this mean you cannot nest more than one? So here you have explicitly exec policy row, exec policy call. I mean, suppose you have a three-dimensional thing that you want to iterate over. Can you do that?
Yeah.
What would you specify?
Go ahead.
Well, yeah, I think you're going, yeah, you were going to answer it. You would just specify a third iteration space, and you would add another for statement.
Okay, but I guess what I'm asking is, row and column implies a two-dimensional mindset.
Yes.
So what would I spend, I mean,
Oh, those are just kind of generic labels.
I see, thank you.
Yeah, so.
Oh, yes.
Those would be like sequential execution.
Got it, thank you.
Sorry.
Yeah, this just ties back to the matrix multiplication example. Yeah.
So what does 1 and 0 mean here?
So that corresponds to, so what's happening here is we're tying that for loop to yeah, so it's the variable and also the iteration space. So 0 so that 0, we have the for loop, you have that column range, and then you have that iteration variable there.
It's the index of the tuple.
Right. Okay, good.
So the next slide, because the 0 is still typed to call and the 1 is still typed to row, all your tuples and stuff from the previous slide are still okay. It's just that the order of the for loops is swapped.
Exactly.
So as Arturo said, you would do the same thing if you had like an I loop nested inside J loop and you just swap those statements. That's what you're doing.
Okay, so so the constructs that are used to make up this kernel policy, essentially it comprises a simple domain-specific language that only relies on standard C++11 support. So the idea here is to build a kernel policy, use statements and statement list, right? A statement is an action, right? You can choose to execute a loop, right? So in this case, for is going to execute a loop. You can invoke a lambda using the lambda statement, and then you can, if you have a threaded policy, then you can also choose to synchronize threads, right? And we have CUDA sync threads, and then we also have OpenMP sync threads. So essentially, these are the building blocks for a statement list. And the way you can think of this is just processing a sequence of commands, essentially. So your kernel policy is a statement list. Okay, so in this example below, right, what's essentially going on is you can think of having a for loop. You have a lambda that's carrying out some sort of action, and then you have another for loop after that action that carries out another action, a lambda, right? And then we have another example in a couple of slides that is essentially going to show the analogs between writing C-style loops and these policies. Yes.
What's the signature of the lambda 0 versus the lambda 1? The arguments.
For this particular case, they have to have the identical arguments, but we have an API that allows you to select which arguments to pass in each lambda. It's more robust.
Yes, but we won't go over it in this.
I don't think we can do anything because that's more complicated.
It's also, yeah.
But for these examples, they all have to have the same argument list and the same order, even though we don't have to use all of them. Okay, well, we support it.
So Raja provides a variety of statements. So we won't discuss all of them in this tutorial, but we'll discuss some of them. And of course, if you pull up the user guide, there's a complete listing of available statement types, and there's a description of what they do. So we're going to jump into loop transformations. So I'm going to talk about loop tiling. And just as a refresher, So loop tiling is a loop transformation, and the basic underlying idea of loop tiling is that you take your iteration space, you chop it up into chunks, you chop it into tiles, and then rather than just traversing your old iteration space, you traverse tiles, and then in the tile, you traverse each of the values in the tile, right? So one of the reasons you would do this is to ensure that data used in loops stays in cache until it's reused. You can also apply this technique to utilize different levels of memory, and the tile size ends up being a performance tuning parameter. So depending on what platform you're on, you may want to adjust what the tile size is. And then just for completeness, I'm going to illustrate an example of taking a regular loop and applying the tiling transformation. So on the left, we have a standard loop. It ranges, the iteration space ranges from 0 to n. And then on the right, we've done some tiling. So behind the scenes, we have a tile dimension, and we have a number of tiles. And the basic idea here is you loop over the tiles, then you loop over the entries in the tile, and then because I've broken up my iteration space, then I have to calculate what my global index is. Okay. So these tiling algorithms can be applied, these tiling transformations can be applied to a variety of algorithms. So one basic example is doing a matrix transpose. And the idea behind applying tiling to matrix transpose is to simply consider your input matrix, break it up into a collection of tiles, and then loop over each of the tiles and transpose the data in the tile into an output matrix, right? So here in A, our tile is 2 by 2, and then when we're writing out, we just transpose the data in the tile. So, this is you can use this technique to improve spatial and temporal locality of data access. And then you can also choose to store the data of the tile in CPU stack memory or GPU shared memory for further improved performance. So we're going to dive into this particular example. First, we're going to consider doing the matrix transpose without storing the local tile, right? And here on the slide, we have the example written in a C-style implementation. So it's exactly as you would expect, right? You have an input matrix A. You have some fixed tile size. You loop over the tiles, and then you loop over the entries in the tile, right? You have to do your global index calculation. And in the scenario that the matrix is not divisible by the tile size, then you have to do some bounds checking, right? So that's that very last statement there. So we can also do this in Raja. So Raja tiling policies have very analogous structure. In a similar fashion, we have a statement called tile, right? So it takes an iteration space from the segment from the tuple, breaks it up into tiles of fixed size, and you specify the execution policy, like how do you traverse the tiles. And here in this example, we're doing it sequentially. And then you have your second set of loops that traverse the entries within the tile. So here we simply use another set of 4 statements, and then to create a policy to do matrix transpose, we simply encapsulate the action in this particular lambda. So nested loop constructs inside tile statements are the same as the non-tiled case. So if you use Raja to do this tiling, it's the case that you don't need to actually calculate global indices. Raja will give that to calculate those for you. So let's try it out. Exercise 7, tiled matrix transpose. So if you look in the exercises, exercise 7 is exactly this. It contains a C-style sequential implementation of tiled matrix transpose. In this exercise, we give you the tiling policy, and all you have to do is write the kernel that takes in the policy using Raja. So just a couple notes. Bounds check are not needed. Raja tiling statements mask out of bounds indices, and what's being passed into the Lambda are the global indices, right? So you don't need to compute those manually. So why don't we take like 15 minutes? Me and Rich will walk around. Feel free to flag us down if you want to chat about anything. Okay, not too bad, right? Okay, so me and Rich will be around. If you guys want to chat, feel free to flag us and we'll chat about it. So the next thing I'm going to be talking about is local data. So as it turns out, many algorithms require non-perfectly nested loops to improve performance. So to this point, we've only been looking at perfectly nested loops, loop nest with no intervening code between them. But if we step back and recall the matrix multiplication example, right, so this setup step of initializing our scalar value right there, dot to 0, actually breaks our perfectly nested loops. So then the question becomes, how can we write this as a unified Raja kernel that is portable? So if we look at the structure of the loops, we can describe the actions. We can essentially create a mirror policy with lambdas that essentially capture the action of what the C implementation is doing, right? So what do we have? What we have is a pair of for loops, right? So on the right, we have loops that corresponds to the row and column loops. We have a lambda that initializes our value to 0. And then we have another for loop that calculates the dot product, right? And then in that for loop, we have another action, right? So we can represent that using a lambda. And then finally, we have the operation to write out to our global array. Right? And we can express that using an action as well. So if we were to construct a kernel policy that encapsulates these actions, the kernel would look something like this. So we wouldn't use the standard kernel. We would use the extension kernel param to pass in an additional tuple for thread local variables and kernel local arrays. So the thing to note here is that we're using kernel param, right? The first tuple takes the iteration spaces for the column, the row, and the dot loops, and then we pass in a scalar value into a second tuple that's going to be used for thread local variables, right? And then those three actions can be represented using lambdas. So the first lambda is going to initialize the scalar value to 0. The second lambda calculates the dot product. And then the last lambda does the write out to global memory, right? So in this case, all lambdas have the same arguments, but it's the case that you don't have to use all the arguments, right? So in Raja, we provide other statement types to make this cleaner. So just to bring it back to the policy, this is the execution policy that you would use to compose such statements and define the kernel execution pattern, right? So you have your two loops. You have the lambda that does a setup step that initializes to 0, the scalar value to 0. Then you have another for loop that actually does the dot product calculation. And then you have the last lambda that writes out to global memory. Right, so we aim to make this analogous to nested for loops and other statements in a C-style loop nest. So with such a policy, we have the flexibility to change how we want to run the loops. So if I want parallelism on both the row and the column loops, we can use an OMP parallel collapse execution policy, right? This will collapse both iteration spaces and just create a single parallel region. and then distribute the iterations 1 and 0 across CPU threads. We can also just change up the policy to launch the code as a CUDA kernel, right? So what would have to be adjusted is that we have to add in an additional statement, CUDA kernel, and then we have the flexibility to map loops onto CUDA blocks and CUDA threads, right? So what's going on here is that the policy is distributing row indices over CUDA thread blocks and column indices over threads in each block.
Question.
Yes?
What happens if I specify statement : lambda 3?
Well, you would have to specify a third lambda if you want something to happen.
Well,
It won't compile.
So I'll get a wall of template error compile time.
No, it'll tell you that there is no, it'll basically say there is no third entry defined in the tuple. That's a problem with a lot of this stuff, right? You can get the matrix, right? Showering down with error messages that go on for pages and pages. Right,
Sort of
so,
innate with C++ templates.
right, so we try to improve that continually using static asserts, trying to come up with a framework to give people useful error messages and things like that, yeah.
Okay.
But with this templated code, you're never gonna cover everything because some user will try something that you hadn't anticipated, right, oftentimes. So you try to do the best you can to cover, you know.
Do you have a collapse clause for CUDA? The collapse execution policy? So could I write the first thing, the one before, with a simple, like, CUDA statement?
No, I don't think so.
We don't have we used to have a kernel collapse policy, but we got rid of it. Well,
How do you?
we still have it.
I don't think we do.
I think we took it out.
Yeah.
Because that was in iteration 2 of this API, and we decided we didn't like that.
General question: who decides, in your teams, how do you choose the correct policies for all of this? The correct execution policies, right? Is that
You mean on the application teams?
Yeah, I mean, the application teams have to define this thing at some place, right?
That's right.
Yes.
And they have to decide what execution policies to stick in there, right? And I'm just imagining right now I throw that over the fence to my physics developers and they're gonna go.
Yeah. Typically, our code physicists are not working at this level.
Okay.
We have typically each team has some optimization experts that are kind of very fluent in Raja, or somebody who's actually a Raja developer. That's our working model.
And we essentially set these policies somewhere, and then everybody just uses them throughout the rest of the code in the physics part.
Yeah, that's right. And I mean, that's kind of I mean, you see that too with some of your users, right? You need to give them expertise in how to use things, right? We have a a tighter feedback loop with our
Yeah. Okay.
Okay. All right, so back to the matrix transpose loop tiling example. So I mentioned when we were doing tiling for matrix transpose that we have the option of storing the tile data in a local array, right? So like in the CPU, it can be like stack memory. So you can do that for performance reasons. If you know about shared memory on a GPU, you can use GPU shared memory. And I want to visit this example because I want to illustrate the pattern that you would need to do this in C++, right? So on the screen, we have the C implementation of matrix transpose with loop tiling. Here, I've allocated a buffer essentially inside my loops that traverse the number of tiles that I need. I have a set of for loops that read in data from my big matrix into my local tile. And then I have another set of loops after I'm done loading the information. I move it back onto the transposed to my output matrix. So a quick note about this. It's really important. Scope is very important when it comes to parallel computing. So depending on how you're going to parallelize these loops, you need different requirements for access requirements for your local data. So if you choose to parallelize the traversal of the tiles, then it's necessary that your tile is thread private to each of the threads, right? So if you were to initialize that tile outside of the parallel for region, then it would be shared across the threads, and you wouldn't get the correct behavior that you would want, right? But on the other side, if we're going to parallelize the inner loops, then we have the requirement that the buffer should be accessible by all the threads, so we can carry out the transpose.
But it's important to note that each thread would be accessing a different entry, writing into a different entry in that matrix tile, right? So there's no problem.
Right. Okay, so Raja has a feature to do these type of operations. So Raja has the local array type, and it's used to manage these cases in a portable manner, right? So this is a particular type. And here we're defining the type using this local array template. So we template based on our data type. We can choose a permutation, and we pass in a size list. So at compile time, we need to know how big our local array needs to be. So just by defining the type, we've actually not initialized any, we actually haven't allocated any of the memory. The local array is actually initialized for use in a kernel using the init local memory statement, right? So when you're actually executing the policy, that's when the memory allocation gets done. So this initialization requires a memory policy that binds the local array object to a slot in the parameter tuple. So you also have to specify where in your parameter tuple this local array type lives, so you can identify it and initialize the memory that corresponds to it. So we currently have 3 different policies for local arrays. We have a CPU tile memory, which essentially allocates memory on the CPU stack. We have CUDA shared memory, which allocates memory in CUDA shared memory. And then we have CUDA thread mem. So this is going to allocate memory local to a CUDA thread. Okay, so the accompanying kernel for the matrix transpose with local array uses the Raja local array type. And then the way this works is when you're actually defining your kernel, you're going to use kernel param. The first tuple holds the iteration spaces, and then the second tuple is going to hold 3 things. It's going to hold placeholder values, and these placeholder values are used to retrieve local indices for your local tile, and then you pass in the actual tile array object, right? And then when you're actually doing the transposition, right, so this first lambda is going to move data from the global matrix onto a local tile, and you need different indices, right, because your local tile is smaller than your global matrix, and then your second lambda does the write out from, it reads the data from the local tile onto the output matrix.
So, yeah, one thing to notice here is that it looks complicated, and it kind of is. And this is the default implementation where all of the lambdas have the exact same arguments. But if you look at the order of the arguments to the lambdas, they're just basically following through the tuples, right? You've got a column for the column, global column index, you've got the row for the row, you've got the X and Y local tile indices, the local tile, and then the shared memory tile at the end, right? So it's just in that same order of putting those tuples together.
Okay. So exercise 8. So matrix transpose with a local array. So exercise 8 contains a C-style sequential implementation of the matrix transpose, which stores tile data in the local array. You'll also find the actual kernel that does the transpose. So the task here is to implement the associated Raja policy for the OpenMP Raja kernel variants of matrix transpose. And if you can do it for CUDA, then try doing that. Some notes. You will need both the local tile index as well as the global index. And rather than using the standard for statement, you're going to have to use the for I count statement to generate local tile indices. And this is going to be passed in into the lambda. So you also need to initialize the local memory, and you can do this using the init local memory statement. So why don't we take 15 minutes to try this? Me and Rich will be around. Feel free to flag us down. You guys have the exercise. The solution is there. If you want to talk to us, yeah, the solution's on the next slide. Feel free to talk to us afterwards. But just to keep it moving along.
Why don't you just kind of step through it?
Oh, okay. Sure. So just to step over the kernel policy, right? What's going on here is that we have a policy such that we're choosing to tile our outer loops, right? So we're choosing to traverse the different tiles in the row and the column. And then after we kicked off our loops, we initialize the local memory, right? And then we have a second set of loops that actually does the reading from the input matrix onto the local memory tile, right? And the action of these loops is captured in the lambda. We're also using the for I count to retrieve the local tile index, right? So after we've done the loading, we then read from the local tile, and then we output back into the global array, right? And the actual work is captured by the lambda right there. Right, and these are just closing statements.
Also, to point out those two inner loops, the loop order is switched. So basically, when you're reading in the first one, that first chunk, for I count 1 and then for I count 0, your stride 1 through your source array. And then for the second one, your stride 1 when you're writing into your destination array. Okay, so you can do that kind of stuff, right, to make your memory accesses more efficient.
Yeah, and actually that gets done in the C version as well. So it's just a direct translation over to Raja. Okay, so Raja support for complex loops, right? We have strong support with the Sequential, SIMD, OpenMP, CPU, and CUDA backends. In progress, OpenMP Target, the TBB, and the HIP's coming soon. And then the last thing I want to touch on is application considerations. So for those who work on large applications, whenever you introduce new technology, you kind of have to consider your application's characteristics and constraints. If you want to use something like Raja, you have to decide how it's going to fit in, where is it going to be used, what loops. Right, profiling your code is very important. You can ask questions like, do few kernels dominate runtime? There'll be certain applications where no one kernel actually takes the significant fraction of runtime, right? All kernels take roughly around the same. You can ask questions like, can you afford to maintain multiple highly optimized architecture-specific versions of important kernels, right? Can you maintain a really optimized CUDA or HIP version? And then do you require truly portable single source implementations? So I just want to go over how some folks at Livermore have been using Raja. So one thing you can do is you can construct a taxonomy of algorithm patterns and loop structures in your code. Right? You can try grouping loops into types of two classes. So those classes of loops can use the same execution policies. If you have a large code with many kernels, it may be easier to port to Raja if you define your policy types in a header file and then apply each to many loops. And I think Rich showed this earlier in his part of the talk. There are many applications where developers like having something that's closer to a domain-specific language. And we see this at Livermore as well. Sometimes people will create a lightweight wrapper around Raja. So questions you can ask is, how important is it that you preserve the look and feel of your code, right? Like semantics is very important. Right, so how comfortable is your team with software disruption and using C++ templates? Sometimes you work in these code teams where maybe you have people who are more physicists than computer scientists, right? So, depending on who you work with, you can ask questions such as, is it important that you limit implementation details to your computer science and performance tuning experts? So a couple more things. Right, Raja promotes flexibility via type parameterization. So we believe in defining type aliases in header files, right? Like that, everything is in one file and it's easy to change. It's easy to explore implementation choices in a larger code base. It also reduces source code disruption. An example of this is using aliases to assign execution policies, right? So if you have loops that have to traverse a number of elements, right, you can define a policy for this, and then you could just pop it into the for all method as so. Right, so it's up to application developers to determine an appropriate loop taxonomy and policy selection for their code. So something we've learned over time is that performance portability takes effort. Raja, like any programming model, is an enabling technology. Right, understanding your code, loop characterization, and performance tuning are very much a manual process. Good tools are essential. It's really important to look at things like memory motion and access patterns, right? How you're accessing data has a huge plays an important role in performance, so it's important to pay attention to them. This is true across the board with any type of architecture. So it also may be that application coding styles may need to change regardless of programming model, right? So as we're going from sequential to parallelism, right, it may be essential that we refactor algorithms to ensure correct parallel execution. If you can express some of your algorithms as reductions or scans, right, things that we know how to run in parallel, right, this makes it easier to do things in parallel. In the case that we're introducing threads, things you can do is you can move variable declarations to innermost scope, to the innermost scope to avoid threading issues. And a couple considerations is that virtual functions and C++ STL are problematic for GPU execution, right? So we found that simpler is almost always better, right? So sticking with simple types and arrays makes it easy to be portable. And the wrap up. So this is the stoplight chart. Rich showed it in the beginning of the talk. I'm showing it again just to go over the type of features that Raja has, right? We have support for things like simple loops, reductions, segments, and index sets, atomic scans, complex loops, layouts, and views, right? We're working on filling this in. We want to try to make it all green. HIP is coming soon. We're reviewing a pull request. And I just want to point out a few more things. So there's materials that are supplemental to this tutorial, right? So the examples you guys have, you guys know where our GitHub repository is, but if you go into our GitHub, you'll find the Raja repo. There's many similar examples. They're all in the examples folder. There's a user guide. The topics that we discussed today, it was all there. And it's available on Read the Docs. There's also a link in the Raja GitHub repository. And then there's also some related software. The Raja Performance Suite, right? We care about performance. So what we do is we monitor how Raja behaves compared to non-Raja forms, like if you write things in a native C or CUDA implementation. We have variants of our algorithms that use Raja, and then we write the counterparts in Sequential OpenMP target CUDA. And we monitor the performance across different compilers. We see which compilers do well and which ones we like. And this is important for us because it gives us essentially an environment so we can interact with vendors and have discussions on what we're seeing. And it's useful for benchmarking for Coral and Coral 2 systems. This is also available on GitHub, so if you're interested in trying this out in your computing environment, you can just grab it and run it. Some more related software, Chai. Chai was mentioned earlier, right? This is this is a tool that can do data copies to different memory spaces behind the scenes. So take care of it for you. You won't have to do CUDA malloc or CUDA mem copies and things like that. It's designed to work with Raja, and it could be used with other Lambda-based C++ abstractions. And this is also available on GitHub, so feel free to grab it. So again, we appreciate your feedback. If you have any comments, questions, suggestions, feel free to flag us down. We'll talk to you. We're happy to chat. You can also join our Google group, or if you want, you can just contact us via email. That's our email. Anyone in the Raja team will see that. All right, so with that, I conclude, and thank you for your attention and participation.
Hi. Yeah, so thank you for the presentation. Let's suppose we have a multi-core CPU and 3 GPUs, and I have a 3-nested loop to parallelize. So using the execution policies, it is possible to simultaneously utilize both the devices, both different kind of devices? No?
Not currently in a single kernel, no. Well, you'd also have the data management issue too, right? You'd have to chop up your data and somehow avoid, moving it back and forth.
So if I have to only use 3 GPUs and I don't want to use CPU for my computation, so the execution policy will handle only 1 GPU or all the 3 GPUs?
No, one.
Only one.
Yeah, so typically it's most easy for applications to basically have one MPI rank per GPU, right? Otherwise you have to do a lot of gymnastics to coordinate data. You probably have looked into that, right? We don't have a lot of experience with any of our applications actually doing that successfully.
Well, once again, thank you guys.